So measuring dispersion then, there are two main options to go for, the variance and the standard deviation. So if you look at the first equation, this gives you the equation for the variance. Now this is, the first one is the sort of full definition. There's often mistakes here in finance and business maths books, okay, but it should have the n-1 rather than the n term. Second formula. So often what you'll find is even if the sort of financial textbook has got the right formula, doesn't necessarily give you the simplified version which you can use for practical calculation. And then the variance and the standard deviation, as we said before, give you two sides of the same coin. So if you calculate the variance, then you take the square root, and this gives you the standard deviation. Okay, let me just repeat one more time. So there are two formulas here. So the first one gives you the technical definition of the standard deviation, and then the second one gives you the actual practical calculation formula, which does give you some simplification. This isn't always as well as clearly as expressed as it should be in books on corporate finance, for instance. Okay, so what you should find is these formulas probably easier than they might first. So in terms of the variance and standard deviation then, so the practical calculation formula are given in the top half of the slide, and again this is something that's easy to overlook in terms of the application of these formula in corporate finance. So I want to give you a sort of detailed hand calculation example in the second half of the slide. So we've got the data in the there. In order to calculate the variance, the first thing is to calculate the mean. You calculate the mean by just adding up all the observations in the sample divided by the sample size. This thing here, sum equals 1 to n of xi squared. This is just summing the squares of the observations sample. So it might look a bit confusing because it's using formal algebraic notation, but it's a lot simpler than it might first appear. Just plug these numbers into the formula one at a time. Now I ought to say here that please don't rush this, because this is an easy way for students to make a mistake if you sort of rush simple numbers into the formula. So it's like this, and I would make sure that you don't rush all the calculations here, and then the standard deviation is just the square root of the variance. So the variance and standard deviation are again just two sides of the same coin. Way of measuring spread, other than the variance and standard deviation, is to talk about quartiles and the interquartile range. So we've discussed the median before. The median is the 0.5 point or the halfway mark of the ordered data. You can define other quartiles and infinitely many other quantiles similarly. So the basic idea then is you sort of split the sample up into sort of nice numbers. The median is the second quartile and the halfway point, or the 50% quantile, and then you can similarly define the lower quartile to be the 0.25 point or the quarter way mark of the ordered data, and the upper quartile to be the 0.75 point or the 3/4 mark of the ordered data. And then what you can do once you've done that is to define a measure of dispersion or spread as the interquartile range, which is the difference between the upper and lower quartiles. So this interquartile range should always be positive, and the higher the interquartile range, the more spread out the data is in the sample. Okay, so it's an extension of the idea behind the median, but what you're doing in this case is to try and give you an alternative measure of how far spread out your data set is. In terms of the interquartile range, then the key formula to remember is simply that the interquartile range is the upper quartile minus the lower quartile. This gives you a measure of the dispersion or spread of the data. It's sometimes thought that this gives you a more accurate measure of spread in a data set if your data set contains large or extreme outlying observations. So this might be the case, for instance, with financial data like stock price return data. So it might be that the interquartile range gives you a better summary of the amount of spread in a data set than the variance or standard deviation for financial data. Now I ought to say here that the basic formula that I want you to remember is the interquartile range is just the difference between the upper quartile and the lower quartile. Now it turns out that these and lower quartiles are actually deceptively difficult to calculate. So it's easy to calculate these in Excel, but it's actually quite involved to do this by hand. Okay, the formulas involved are quite complex, and they're much more complex than some business mathematics books I've seen actually acknowledge. Okay, so interquartile range is the difference between the upper quartile and lower quartile, but the upper and lower quartiles. So at the risk of repeating myself again then, so the key formula you have to remember is the interquartile range is just the upper quartile minus the lower quartile. So calculating quartiles is deceptively evolved. Many different formulas are given, and the polite way of putting this is that the standard of business mathematics texts and other statistical study guides can be very varied. Okay, this is a public forum, this is probably the right way to describe it. In a private forum I might be less polite. I was, for instance, shocked when on my previous institutions study guide students were expected to buy and to study from gave the wrong formula for calculating these quartiles. So I don't expect people to calculate quartiles. It's more important to be able to do this by computer. Give some Excel examples later in this lecture, and I'll put some Excel examples on the module page on Canvas. But calculation of quartiles and interquartile range can be deceptively involved. Now the maths of this uses something called pivots, and it's easy to make mistakes here. Okay, as I said before, I've seen all sorts of mistakes in business textbooks on this, so this isn't quite as dibbly-dobbly nice and easy as you might otherwise imagine. So I have included this here as a potential measure of spread or dispersion in the data, but the range is a little bit rubbish really, and is probably not as good summary of the amount of spread in a data set as either the variance or the standard deviation or the interquartile range. Okay, the range is simply given by the difference between the maximum and the minimum values. So the idea is that as the difference between the maximum and the minimum increases, the range increases, and so in this sense the data becomes more spread out as this value of the range increases. But it is quite a fairly measure data, and I think ordinarily you would expect that the variance or the standard deviation or the interquartile range would give better summaries. I've included it here because it's calculated in a similar way to the interquartile range in Excel. So we've got this sort of numerical example between the brackets. The range would just be the maximum value minus the minimum value. So if you squint a bit looking at this brackets, the maximum value is 22, 1, now to 22 minus 1 is 21, so the range for this data set is 21. Okay, so normally that's a measure of spread, but the variance and the standard deviation interquartile range usually better. But I wanted to sort of give you the Excel commands you need to in order to calculate the variance and standard deviation. So suppose you've got data in cells and you want to calculate the variance. So what you would do is click on the insert formula icon FX, choose category statistical. Then what you should do here is select S and then press OK. So different variants of this formula in Excel. The right ones to use here would be var.s, not var.p. Press OK, and then you would cells A1 to A10 in the box title number 1. It's essentially the same process in order to calculate the standard deviation. You just need to put in S rather than S in P. Now again, I ought to make the point here is that there's different versions of this thing floating around. Now you should, for this course, be using var.s and sdev.s, not var.p and sdev.p. Different books do this differently, but in my view, the .s ones are the right ones to use here. It's more consistent with proper statistics. If you use var.p or sdev.p, there's actually a danger that you underestimate the amount of spread that is really in your data set. Calculation of the range and interquartile range works in roughly the same way. So you've got the data set in cells A1 to A10, want to calculate interquartile range. Now this does get a little bit clunky because Excel isn't a high-level programming language, so what you have to do is calculate the upper quartile, then the lower quartile, and then take the difference. You can't calculate the interquartile range in one step. Similarly, if you want to calculate the range, you need to find the maximum, then the minimum, and then calculate the difference. You can't calculate the range directly using the available formula. So in order to do the interquartile range, so A10, click on the formula icon, choose the category statistical, C, A, tells the data is in the box entitled A, in the box marked quartz, exactly the same lower quartile, and then if you subtract one from the other, you can then calculate the interquartile range, and the thing to watch out when you do this is the interquartile range should be positive, and then in order to calculate the range, same steps, you would need in step 5 to calculate the maximum, and then 0 in step 5 to calculate the minimum. The difference will give you the range. So I wanted to sort of motivate the next topic pictorially with simple graphical analyses. So these are not necessarily highfalutin, they should be a version of what you've seen at high school. Okay, but I just wanted to sort of emphasize here that regression, although it is an important part of financial research and indeed mathematics and statistics, in a lot of ways it is just a sort of harder version of high school maths. So suppose you've got two variables, x and y. X might be the interest rate, y would be the GDP. So there's two obvious questions to ask. What happens to y? Does it increase, decrease, or nothing at all? Similarly, increases, what happens to x? Does it increase, decrease, or nothing at all? And I said there that these basic questions lead to a core area of statistics entitled regression. Now all that is happening here, what I really wanted to sort of try and get across is that although there is some mathematics and statistics involved, you've got something that you can represent graphically, and I kind of think it's much more helpful when, although you might have lots of equations and hard mathematical concepts kicking about, if there's an underlying graph that illustrates it all, hopefully that should be a bit easier. And there's lots of repetition here from topics that you'll have seen before in high school maths. So, technically speaking, correlation is not causation, but the basic idea is as follows. So if two variables x and y are positively correlated, then as x increases, y increases. Equivalently, as x decreases, y decreases. So you will have seen versions of this at high school maths before, so what I want to sort of get across to you here is that although regression is a serious subject, you know, its roots are fundamental and a repetition of some material from high school maths. An obvious example I thought to try and illustrate this might be if you're looking at, say, the effect of petrol prices on grocery prices. So if X is petrol prices and Y is grocery prices, then you might naturally expect that as the petrol price increases, the grocery price will also decrease. Equivalently, I suppose if you're a government and you're wanting to sort of make grocery prices as low as possible, you might look to incorporate policy measures that would decrease the fuel price. Okay, so lots and lots of examples finance and economics, how these basic ideas will apply, give you graphical illustration of these concepts